everyone, wherever you are. Welcome to another Dynamics Committee seminar series. I'm very proud to introduce our committee leadership who has brought you this seminar series. Myself, I'm Hamad Ibrahimian. I'm the chair of Dynamics Committee, along with Professor Manolis Chatsi at the University of Oxford, who is the vice chair, Professor Yanis Kuchumzoglu at Columbia University, our chair of student paper competition. And last but not least, Professor Marianne Guterres-Soto, our DEI delegate who has specifically arranged and coordinated this seminar series. Also, special thanks goes to Tisha Kramer from EMI, who has arranged all the logistics, and we are here because of her today. So thank you so much, Tisha. Would like to bring up a few notes, and then I will pass it on to Marianne to introduce our wonderful speakers. So Dynamics Committee, we have several activities. I encourage everyone to visit our webpage. If you Google EMI Dynamics Committee, we have a webpage with all the activities and details in there. If you are not a member of our committee, I strongly suggest and recommend you to apply to become a member. The membership conditions are on the website. If you are willing to participate in this seminar series as a speaker, that option is available. We have other programs, including mentoring program, which might be very useful, especially for young and early career faculties or colleagues who want to pursue academic career. So please take advantage of these opportunities. And of course, we're gonna have a student paper competition at the upcoming EMI in Anaheim. If you are interested in helping us as a judge, if you're a part of the committee, if you're a member of a committee and willing to help us as a judge, again, communicate with us. Our contact information are online. With that, again, thank you so much, everyone, for joining. I will pass it on to Professor Guterres-Soto to introduce our wonderful speakers. Thank you.
We are delighted to have two wonderful speakers. So just so that we're gonna have the first presentation by Dr. Yuguang Fu. If you can put your presentation, then we'll go ahead and introduce you. He will give the first part of the presentation for about 25 minutes. Then we'll have Dr. Lauren Linderman right after. And once both of our presenters finish their presentations, then we'll open it up for questions and answers. If you have questions during the presentation, please put them on the chat so that we can address them at the end. So help me welcome our first presenter. So we have Dr. Fu. He's an assistant professor at the School of Civil and Environmental Engineering at Nanyang Technological University. Dr. Fu was a postdoctoral research associate in the Resilient Extraterrestrial Habitats Institute at Purdue University. He also worked as a research scientist at Embedded Technologies to commercialize the sensor technology developed during his PhD study. His research interests include smart sensing, digital twin, artificial intelligence, and their applications in digital construction and infrastructure monitoring. And we are so excited to hear him today on the structural anomaly detection using edge intelligence on vibration-based IoT sensing. Thank you, and let's go ahead and get started.
Thank you, Maria, for introducing me, and also thanks, Hamid, thanks, Manolis, and also thanks, Tisha, for offering this opportunity for me. And good morning, good afternoon, and good evening. Actually, here is in the evening. So it's great pleasure and honor for me to make a presentation here. So my topic is the structural anomaly detection using edge intelligence on vibration-based IoT sensing. As I think Maria already introduced me, so I just quickly go through that. I actually currently in Singapore, and we actually also revitalizing AACE Singapore section with my colleagues. We have around 100 members, I think, including some senior member or even fellows. So we also try to organizing some events as well. Okay, so here's the outline of today's presentation. I will give a brief background and motivation, and then later on talking about vibration-based AIoT. Basically, AIoT is a buzzword. Basically, try to do the combination of AI plus IoT. Yeah, so we will talk about the current prototype development efforts and also the edge intelligence, some brief results. And then we'll talk about structured anomaly detections, algorithms, and applications. Finally, give concluding remarks. Okay, so starting with the background, our civil infrastructure is actually is strengthened or overburdened for a couple of factors. The first one is the aging. Even in Singapore, aging infrastructure is a growing concern, and a lot of infrastructure has more than like 40 or even 50 years old. On the other hand, is actually the growing population. Many people use that, and then maybe the old structure design maybe for a relatively small number of people to use, but these days more and more people are going to get crowded inside the building, so that's also another factor. And lastly is actually the natural hazard like earthquakes and also the human-induced hazard as well, like impacts. So this can actually make our civil infrastructure in the situation that need protection. And good news that I heard that there's a newly released AAC kind of report of the infrastructure. I think the ratings is increased. I think that's a good news. Okay, so from my area, we more using the structural health monitoring, try to help to protect and ensure our infrastructure resilience. This is just a kind of two representative examples. One is using the Y sensor in Qingma and Qingma Bridge in Hong Kong, and on the right-hand side is the Jingdu Bridge in South Korea. But using wireless smart sensors. And in my previous work, I was working with Professor Spencer at University of Illinois. My main work is try to helping to develop the X-Node, the next generation wireless smart sensors. So the key kind of focus try to make sure it is actually can do multitasking. It can also do event trigger sensing, and lastly, it can do kind of cloud-based data management as well. Yeah, so we actually also get some small business innovation research phase 1 grants to commercialize the product for I think railway bridge recognition assessments. So moving forward, after I moved to Singapore, I'm thinking about how do we kind of extend these efforts to be more powerful, more kind of cost effective, for example, for sure, yeah. So and these days people talk about IoT, the AI a lot. So we are thinking about what would be the kind of opportunities offering by introducing this into our existing wireless structured health monitoring system. So one intuitive idea is that since we are talking about IoT, we will have like more kind of a remote monitoring functionalities, and also there are a lot of kind of communication protocol we can leverage. On the other hand, since the current chip and also kind of advancements in electronic engineering, so we can actually put more and more kind of computing into the edge devices, and that actually can make our decentralized or computing is more powerful than before previous like IMO2 or X-Node. So the benefit is that we can make less data for transmission, for fast for SHM results, and in the end we can kind of make the system more compact and more scalable, such that we can actually span our SHM application into not just the signature structure but also traditional or normal structures. Okay. So the other based on the current kind of IoT and devices, there's a growing interest talking about edge intelligence. So basically, edge intelligence is trying to combine the edge computing and artificial intelligence. Basically, we push the traditional computing of AI or machine learning algorithms, models, instead of from the cloud server or workstation, we put that into the edge devices. And that devices has limited resources, like limited memory, limited battery, and et cetera, et cetera. So we need to make sure the algorithm is lightweight. Yeah. So on the left-hand side shows the kind of the traditional way to use the cloud server to do the training of AI and then do inference and eventually go back to, let me use the laser pointer, yeah, and then send the result back to the system. But these days we can actually put model into the edge devices to the training and inference, and then that way we don't need to transmit data, raw data. We actually just transmit the information directly. Yeah, so that's actually introduced the AIoT. Basically, is put AI and IoT into the same device in same small devices. Yeah, on the right hand side shows the challenges. We do some kind of the top 4 challenges, including the limited onboard compute resource, as I mentioned. There could be some power supply issue. We usually use a battery. Yeah, on the right hand side, we also lack of the tools and library, etc., etc. To be clarified, these days people talk about NVIDIA, talk about Jetson. Their devices are very powerful, but still that require more power, and also it's still kind of considered as a small computer, and also expensive compared with if we want to do density and large scale deployments. So our direction is focused on MCU, a microcontroller. So that one is cheap, but it's also it's cheap, power saving, but also resource constraint as well. Yeah, so in that case, it would be more challenging to deploy the machine learning or AI technology onto that. So on the other hand, most applications are general purpose, and we want to move forward for domain specific for structural health monitor and vibration and structural control as well. Yeah. So here's a summary of the research objective for my team. We try to develop a cost-effective and scalable AIoT network to provide early warning hazards, to capture the complete high-quality transient vibration response, to perform onboard structural anomaly detection, structural anomaly assessments, and present the real-time data visualization for end users and make informed decisions. So compared with the traditional one, traditional wireless smart sensor here, we actually will use 5G for communication, and we will totally remove the gateway because each node can function as a gateway, and they actually can also talk with each other more efficiently. So in summary, it will be smarter because we can put AI onto the device. It could be scalable because each one is compact and cheap, and it could also be accessible remotely by the end users. Yeah. So yeah, so here's the talk, and then we'll talk about some kind of ongoing efforts. We're still developing some prototype. We haven't make it a more kind of commercial product yet. So this is the 2 kind of ongoing efforts. We try to STM32 and also ESP32 as the microcontroller, and then based on that, we do some kind of playing to plug and play some kind of devices. So here's the list of list of the hardware component we use, and also most importantly, we are developing the middleware service. We want to develop a tiny SHM middleware such that it can be used for other community researchers together for. We will make it the open source in the future. So in the end, the people, they can just use our middleware, and then they can develop their own application service on top of that easily. Yeah. So and then here I talk about 2 kind of key features powered by edge intelligence. One is the adaptive trigger sensing. So basically, for example, if we want to capture the train crossing events, especially in North America, some trains actually maybe not quite on time. So we cannot just turn on the sensor all the time. So, but how do we can capture this transit event unexpectedly, right? So we need to make the sensor adaptive and smart to turn on and off by themselves. Yeah. So here's actually a base. We implement some like machine learning algorithm on top of that, such that it can more efficient to capture all the events without missing some of them. Yeah. So the other one is the sensor for diagnosis. This has been a very hot topic in the past, but most people focus on data anomaly, but not sensor fault. So we are actually moving forward for sensor fault. We're not just satisfied with the symptom the sickness, but we also try to diagnose what is the source of these symptoms. Yeah, so we actually doing some kind of also onboard process. We try to understand what is happening behind this spike or behind these drifts, and then we based on that we can actually kind of provide this recovery strategy on top of that. On the right-hand side is actually the also the machine learning, but very lightweight. We actually compare with the different strategies. The x-axis is the model size, y-axis is accuracy. Ours one is actually located here, which we can achieve very small model size, but very high accuracy compared with the traditional machine learning algorithms. So in that case, we can actually accurately identify what is the type of data anomaly, and then based on that, we can actually using some strategies to diagnose the force. And for more detail, I will not go in detail, but in bottom side is actually showing the kind of a combination of two anomaly. One is the bias, one is the drift, yeah, and how do we kind of step by step recover that. And also we can try to identify what's the issue behind it. It may be because of temperature overheating, or because of the battery issue, or because of the mountain issue as well. Yeah. So this is basically the tour. Yeah. After we make sure it works, then we can move forward. We can deploy this onto the large scale infrastructure, and the benefit for that is that we can actually let them to process the raw data, and then to send us the early warning if there's something anomaly happens. Yeah. So, and then we can based on this early warning, we can do further inspection afterwards. Yeah. So the first one is the yeah. Later on, I will talk about structure anomaly detections. I will talk about 3 examples quickly. The first one is based on the displacement. So engineers really like displacement, the very intuitive indicator to infer the structure is a good condition or not. Here below shows the 2 examples. One is using the interstructural drift to estimate what is the seismic damage happening based on that. On the right hand side is that showing the lateral displacements for the railway bridge. So that can also use that for the condition assessment indicator. So based on that, we actually develop the reference-free dynamic displacement estimation based on data structure to do the double integration of the acceleration, but we use the kind of a more advanced way such that we can minimize the error due to the integration. We actually also have the high-pass filtering and also optimization algorithm inside it. On the right-hand side shows the comparison between actual and estimation. But the bottleneck is that it actually can only estimate the relative displacement. And so on the right-hand side, we actually also try to estimate what is the accumulating issue or residual error, yeah, based on the integration. So on the right-hand side, we're scaling up the our central earthquake. On the right-hand on the y-axis is the error, and it's growing, but still it could be an indicator for rapid condition assessment or anomaly detection. Yeah, so for that purpose, I think it should be sufficient. So based on that, we actually can use this strategy to do the interstructural drift based on the acceleration measurement from the IoT nodes. Yeah, and then we can use a threshold based rule to classify if the structure is in good condition, for example, threshold number 1, or a bad condition is threshold number 2. Yeah. So next step is we want to make advantage best usage of the AIoT functionality. We want to push the computing into the devices. Yeah. So we actually try different strategies. Basically, we explore different computing steps, like using FFT library, decimate data, etc. So using the existing DSP library. And then also we try to optimize the procedure. And on the right hand side, showing the accuracy, the speed improvements, speed up. Eventually we can save a lot of time and also make it real time. Yeah. So and next step is to do the lab test. We actually, this on the right hand side is showing the 6-story building model, and then we have the 3X node on top of that, and then we deploy the algorithm in the X node. We do the onboard displacement estimation, and then we can also later on do the interstructural drifts afterwards. Yeah, so the accuracy is quite good. So Yeah, so this is the building. We also move forward for the bridge. So the idea is that we can use the lateral displacement of the railway bridge when the train moving across, to use that as the indicator to check if there's a structural anomaly happening. So here we use the Gaussian process regression to build the model. When there's new data come in, we use the statistical process control to check if there's anomaly data or not. If it's not anomaly, then we expand the data and then we update our Gaussian process regression model. If there's anomaly, then we actually send a warning to the users. Yeah. So next step, we also think about how do we deploy that in the IoT node for edge computing. So assuming that we have 2 nodes and we have gateway nodes for the communication for the data processing. So each sensor node, they will do the displacement estimation, and then they will send a maximum value, a single value, just a single value to the gateway nodes, and then the gateway node will do the Gaussian process regression model on board. And on that case, they will further do the kind of anomaly detection to check if for condition assessments. We also consider the temperature effects, try to excluding the environmental effects as well. Yeah. So here's the comparison in terms of the PC computing and also the edge device computing in terms of the arrow. On the left-hand side is the Gaussian process regression prediction. On the right-hand side, the statistic process control. So pretty much every point is measured very well. Yeah. So there's no accumulating error on top of that. And we use that strategy for the bridges, and we do the kind of using the data from several railway bridge in North America, and then we do the modeling parts. And this is just the illustration in terms of how do we use the data from the real deployments. On left-hand side, showing we classify the conditions into green, yellow, and red, indicating the different level of the conditions for the bridge. Yeah. So the next one is talking about the based on the signal discontinuity. Yeah. So basic idea is that if the acceleration measurement is very high frequency and very perfect, there's no noise. If there's a damage happens, the sensor close to that damage will have the discontinuity of the signal will be captured. Yeah, but this is the very ideal case. In reality, we don't have such high frequency measurements, and also we will have the measurement noise on top of that. So then this phenomenon will be totally blurred. There's no way to identify that. So people, they use the blind source separation. They think they're using they first use the wavelet transform. In that case, they can decompose the signal into this type of the discontinuity. Still can see that, but if the noise increase, then they need to use the blind source separation. Yeah, so they consider the damage source is as an indicator. This is a damage source, and then this is a normal source, and then in the real measurement, they mix them together. So using blind source ICA independent components analysis, they can try to isolate the component into this type of the spike-like error signal to indicating the damage location and also the timestamp. Yeah, so. But things that if we keep growing the noise in the figure on the right-hand side, x-axis is the signal noise ratio. If we increase the noise, basically go to the left-hand side, then the original one strategy using blind source separation is no longer effective. You'll find that there's a drop in the green bar here. So we think about can we make it even more noise robust? So in that case, we use the wavelet variational mode decomposition. Yeah. So the idea is that we use variational mode decomposition, try to further excluding the noise effects. That one should be very careful, because if you exclude noise effects, that will also make this spike signal less noticeable. Yeah. So I think VMD is the best strategy, but we compare different signal decomposition strategies. And finally, we find VMD is the best one, such that after we adding that, then the blue bar indicating the success rates of the detection of the damage. We can still maintain very high level number of the detection compared with the traditional one when the noise increase. Basically, the excess should be going to the left-hand side when the noise increase. After that, we also try to think about, can we make it sure autonomous? Because previously, original strategy, we still need to use these human eyes to identify this interesting source as the damage indicator. And sometimes we will have multiple spikes happening in different components. So in that case, it's not easy to realize for autonomous monitoring. So in that case, we also introduce the shapely transform, try to find the most suitable shape that actually can represent the damage indicator. Yeah. So and then based on that, we actually introduce the very simple support vector machine, try to do the classification of the damage. Yeah. So here's the result in terms of numerical simulation, and then we test the WT with transform. I say without VMD and with IMD. With IMD, we can clearly see this damage indicator, but without IMD, we don't see that if the noise increase. On the right hand side is the location of damage. Basically, it shows the I think the number 7 floor. If without VMD, we will see number 7 floor has damage or number 2 floor has damage, but with VMD, we can actually excluding this force net, the wrong case, mistake case, but still focus on this correct one, which is the number 3rd floor has damage. And also this is the online processing. We try to do the classification of damage using the shapely transform and the support vector machine. And then here it shows the correctly identify where is the location of damage and also the timestamp of damage. The location in number 3 floor, and then timestamp is around 99 seconds to 101 seconds. So here's the lab test. The way we simulate the sudden damage is that we put the electric magnet to control this the bar. So if there's some if we disconnect the electricity lines, then there will be a drop of the stiffness in this floor. So representing or emulating the damage happening suddenly. So, and then on the right-hand side, showing the results during the vibration signal, we cannot see anything. But if we do this using our strategy, we can suddenly find this damage indicator and also find the location of damage which in the 4th floor. Yeah. And here's the kind of online processing of this strategy. Yeah, we also make it the onboard processing is quite successful. Lastly example, just to quickly go through. Last example is based. We also try to do some deep learning strategies. So this is the AI Singapore project. I collaborate with Professor Yang Yaowen. I'm the co-PI in this project. So this project has the objective to try to detect the anomaly in the tracks of the tunnel. So traditional way manual inspection is not quite efficient. So we are thinking about, can we use the distributed sensing? We use the DAS distributed acoustic sensing and also plus the spot accelerometer in some critical locations, and use that data to let the AI to the process and then finally find anomalies, including fastener failure, wheel flat, and rail corrugation. Yeah. So yeah, so on the left-hand side, showing the deployment details, we put the DAS system, DAS cable on the rail, and we have IoT node in some locations. This is accelerometers, and then this is wheel flat look like. So for wheel flat, we actually developed an unsupervised machine learning using the autoencoder. So based on we also implement the trigger sensing. Basically, we use the audio to detect if the train move across, and then we will wake up and turn on the sensor to do the data collection. And when the train move by, then we stop the sensing automatically. So for wheel flats, we collaborate with the Metro company to develop deep learning model that detects the wheel flat using the accelerometer signal alone, primary. Specifically, the stop will tell us when the schedule indicating there's a wheel flat, when doesn't have. So we use that information to train our unsupervised machine learning model. And then on the bottom side is actually showing our detection results. The red one is we detect the damage wheel flat and it has been confirmed. And then there's also potential anomaly, which is just listed there for the company to do the further inspection. Yeah. We also do some fastener failure detection. Fastener failure basically we actually manually loosen the bolts, yeah, on the track, and then let the train move across, and then to see what is the vibration signal look like. And what we do here is traditional way use the accelerometer, but it can only deploy some locations, may not be able to cover very large scale fastener. So, but on the other hand, that system, because it's not exactly acceleration measurement, so it's very difficult to interpret results. So what we're doing here is we try to do the cross-model transfer learning. We extract the useful information from the accelerometer, and then to kind of put that to let the DAS data model to learn that feature based on what they learn from the accelerometer. Yeah, so based on this feature learning cross model, then we can actually successfully do fastener failure detection. Yeah, on the right hand side, showing the kind of more detail about which feature actually make a big difference for the failure detection, and actually can give us interpretable idea behind this black box. Yeah, so yeah, so the accuracy is still is actually very high. So we're not showing here. The last example is actually the rail defect. So basically, it's the corrugation on the rail when the train move across many times yeah. So we actually compare with before rail replacements and after rail replacements. Consider the before rail replacement as an anomaly. So we actually also develop a kind of semi-supervised machine learning, and then using the acceleration to do the kind of a wavelet transform, and then to input into these different blocks for this semi-supervised learning, and accuracy also quite good. So it's actually demonstrate our idea is actually very good. Yeah, so overall the system is actually the real-time and also remote connection, and also is actually quite reliable. Yeah. So for concludings, so new vibration-based IoT ART product prototype is actually being developed. We are still developing this next generation. So it's built upon the hardware and also tiny SH middleware. So it's cost-effective and computation efficiency for edge intelligence, and very suitable for large-scale and cost-effective structural anomaly detection. And so we talk about 3 different strategies. One is based on the displacement estimation to do interstructural drift, and also the bridge anomaly detection. And second one is to using the signal discontinuity to do the noise robust blind source separation to find the sudden damage. And lastly is to explore the deep learning involving unsupervised, semi-supervised, and cross-model transfer learning to find the railway track anomaly detection. Yeah. So this is the I would like to thank you the funding support from multiple agency, and also the my colleagues, my students, and my postdocs as well. Thank you for your attention. I'll be happy to answer any questions.
And thank you, Dr. Fu, for such an engaging presentation. We are so delighted that both of our speakers are tackling different challenges with structural health monitoring. So just as a reminder, we'll let questions after both of our speakers have presented. So let's go ahead and invite Dr. Linderman to share her screen so that we can enjoy her talk. So Dr. Lauren Linderman is an associate professor in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota, and the current director of the MAST Laboratory. She earned her PhD in civil engineering from the University of Illinois at Urbana-Champaign in 2013. Dr. Linderman research combines the analytical and experiment studies in the area of smart structures for improving the long-term performance of civil infrastructure to both monitoring and vibration mitigation. And we are delighted to have her here as she's currently the president of the ASCE Minnesota section. And without further ado, let's enjoy this talk.
Well, thank you very much, Marianne, for organizing this, and I appreciate people joining at different hours across the world. As Marianne said, I'm Lauren Linderman. I'm a faculty member at the University of Minnesota. Today, I wanted to talk about essentially a case study where we're looking at the dynamic behavior of some really large sign structures. And I think it's an interesting example of combining field measurements with analysis to understand the behavior and performance of these kind of systems that we're not used to thinking about. Okay. So I'll initially talk about the motivation and then talk about two different sign structures, a dynamic messaging sign and a rural intersection conflict warning sign. For both, I'll talk about the field data we collected, and then the dynamic modeling or the vortex shedding observed, and then finally some conclusions. Oops, sorry. I think I'd be better at this after all these years. The two signs on the left, we have the dynamic messaging sign, as I'm going to refer to this as the DMS. These are message signs that allow for the message to be changed rather than having a static sign. And then they're usually located right to the side of the roadway. And then the RICWA sign, or the rural intersection conflict warning sign, is for kind of non-primary streets approaching a really fast moving road. So it gives the idea that, or the warning to people that are trying to cross, that a fast approaching car is coming. Both of these structures use post-mounted supports that are in the clear zones next to the roadway. And so because of that, they need to be breakaway compatible. So that means if you were to hit the sign, your car would go through it rather than hitting something like a large tree. To do this, there are two types of connections. At the top here, at the top of the W shape, we have a breakaway friction fuse. So this would fracture and then this bends back. And then at the base plate, you have, it snaps through this thin plate. For the RICWIS, you have a tube section that has that's slotted into a base connection with a pin that's designed to fail to hit. And so the big question here is whether the large size and weight of these systems could lead to vibration problems that haven't been seen previously. They actually have seen large vibrations of these RICWIS signs in the field, and they were concerned about that damaging the electronics. And then they're worried about the long-term fatigue viability of these friction fuse with this large sign. So this led us to investigate the wind-induced design loads and behavior, and to address the long-term performance and fatigue life of these structures. In both of these case studies, we looked at we instrumented these structures in the field to identify the wind loading, determine experimentally validated models to ultimately capture some response measure of interest. So in this case, we were looking at the fatigue life for the DMS and the oscillation amplitude for this RICWIS sign. So initially, I'll start by talking about the DMS. This structure is, it's about 3 meters tall to the base of the sign. The sign itself weighs about 1,400 pounds, or about 700 kilograms. And they're a large sign structure supported on two steel dumps that provide the supports. we used a variety of instrumentation. I just got a warning that my internet is unstable, so if you can't hear me, please let me know. We used vane wind anemometers, as well at the top, as well as the mid-height of the sign. We have a gather ambient environmental conditions, 2 accelerometers mounted to the back of the sign to get vibrations in the normal direction, as well as a series of strain gauges. So we had about 70 strain gauges installed at different cross sections along the height of the posts. Kind of the 2 that were the most interesting were the strain gauges at the along the W section. We had strain gauges to capture axial strain in the flanges, as well as a rosette to capture shear strain. And then in the friction fuse connection, we had strain gauges at critical locations, as well as the edges to capture the flow into the plates. In our data collection, we had 2 kind of approaches. The first was to capture slowly varying data. So this was data taken at 5 Hertz that we then computed 5-minute averages. We used this to capture kind of long-term trends, do some kind of debugging, as well as for triggering that triggered the FAST system. We took wind data at 1 Hertz, which is the maximum sampling frequency of these cup and vane anemometers. And then we measured the strain and acceleration at 200 Hertz. Part of this was that we didn't have onboard anti-aliasing filtering, and this allowed us to downsample later. And so the big question here was whether to analyze the system, we needed to use static or dynamic analysis. So traditionally for design of these types of signs, you do not consider wind loading or wind-induced behavior. You do an equivalent static analysis due to a wind pressure. And so we wanted to see how closely this reflected the true behavior of these signs. And to do this, we looked at the force that we would anticipate from the wind loading and how that should compare to the strain that we are observing in the different posts. So what you see on the upper right is the force versus time, and below that is the corresponding strain measurement in one of the axial strain gauges towards the base of the post. So if we have static analysis, we should be able to take the force difference between those 2 x's on the upper right, and that if we applied that equivalent force to our static model or traditional structural analysis, we should get the same corresponding change in strain that we measured. So if we look at that, so what you see here is the strain versus the location of the strain gauge. So we have on the left are the gauges on the I guess the opposite side to the wind. So these are in compression, these are in tension. And we looked at gauges on both the east and the west side of the W section. So here we're seeing purely normal loading. We don't see any torsion. And so we have 0 strain at the middle of the section. And the colored lines are the data, and the black line with bounds that account for potential noise in the system are the expected static strains if you were to do a traditional static analysis. And they don't overlap. They're not terribly far off, but they're not consistent, and we saw this routinely. Now, if we just do a simple dynamic model, so we did a simple analytical model here where we account for the mass of the sign, the gravitational impacts on the stiffness, and did a simple assumed modes model of this continuous support. And we apply that same dynamic wind load, and we look at the corresponding strains, which are now in this gray line. We now see that they overlap with those measured strain gauges. So this to us said, okay, dynamic analysis is really important. And so the mass of the system does have an impact on the response, and you need to conduct dynamic analyses. And so if we want to kind of identify the behavior, an equivalent static analysis isn't going to cut it. And so for our design analysis, we took our experimentally validated DMS model and applied wind loading to then look at our response measure. This requires, if you're actually going to take this to the design level, this requires understanding the wind loading that you're actually going to apply to your dynamic model and how that will relate to the fatigue detailing. And so I'm going to talk a little bit about how we came up with our wind spectrum that we use to create our design level wind loading. So here, what I have plotted is the spectral velocity density of the field data for the large events that we measured. And they were averaged over the events that we saw compared to wind spectrums. So we compared these with 3 classic wind spectrums that you use to characterize the wind demand. And here you see the Davenport spectrum, where all we did was use a terrain factor for this kind of unobstructed landscape, as well as the mean wind speed. And the Davenport spectrum closely matched our field data. And so we were confident that we could use this to reflect our wind loading. We then scaled up this Davenport spectrum to the mean hourly wind speed with a 0.01% exceedance level. This is the current approach or the probability of exceedance that's used in the AASHTO design code. And so we then created a Davenport spectrum with this wind speed. We then applied our band-limited white noise through a Davenport spectrum to generate simulated wind time histories, where we could get the variation in the wind with time. This is then applied to create pressure function. Typically, you would only look at the variation in the wind and the impact on the tension and the fatigue detail. But in this case, we thought that the gravity load of the large mass of the sign panel might actually counteract some of those tension forces. And so we also accounted for not just the variation or that kind of V of T, but as well as the mean wind speed. So we could do an analysis that incorporated the gravity demands. And so if we look at a typical SN curve for this detailing, for this fatigue category, the continuous fatigue limit is 7 KSI. So if you're below that stress limit and tension, you should have an infinite fatigue life for this category D type detail. We actually found from our model that we had a peak stress demand of almost 10 KSI. And this was significantly larger than the stress demand under an equivalent static analysis, which peaked at about 6 KSI. And so you can take this approach. So for 10 KSI, we have about 2 × 10⁶ cycles for our fatigue life. So we take our 10 KSI. We then looked at the instances of 1 second speeds above the hourly limit wind speed. And we translated that to a yearly incident of hourly wind speed beyond the limit state wind speed. So this is a pretty conservative assumption that we're going from 1 second speeds to hourly speeds beyond the limit state wind. And then counted those events. We assume those events were assumed to last the same length as our FEM analysis, and then assume that we had about 4 cycles per second of response. So that gives us the number of cycles that would exceed this stress in a typical year. So it was very conservative steps along each path. So we found in each year, we could have about 84,000 cycles above this fatigue limit. This gives us a fatigue life of 24 years. Now, in the life of this sign, that is essentially an infinite fatigue life. You would likely replace this sign at that point or before that point. But this does show that we no longer satisfy these traditional limits with a static analysis, and a dynamic analysis is needed. We could extend this to other signs. There's a variety of sign architectures, and look at the potential dynamic amplification that you would get from incorporating this large mass in the response. We then looked at the RICLIS, where here we weren't necessarily concerned about fatigue, but we were concerned about oscillation amplitude. So these structures are about 4 meters tall total. They have a 1 meter by 1 meter sign panel that weighs about 75 pounds. I apologize for the mixture of units. These structures use this kind of corrugated metal tube. So because of that, we didn't implement strain gauges. Instead, we used displacement measurements on the posts, as well as accelerometers on the back of the sign to capture normal vibration as well as torsion. And then we also had an anemometer, a cup and vein anemometer, and temperature sensor placed to the side outside of the wake of the response. Similar to the DMS, we had two approaches to our acquisition. We took our slowly varying data to generate 5-minute averages and trigger our fast system, which was again capturing our wind data at 1 Hertz and our displacement and acceleration data at about 100 Hertz. In addition to our field experiments, we also did some small scale lab experiments. At the St. Anthony Falls lab here with my colleagues in water resources, we looked at a 1 to 18 stainless steel scale model of our sign structure. And we put this scale model through 2 types of tests. One was a tow tank, where we can capture the drag as well as look at the wake in the water. And then in the wind tunnel, we have our small scale model that's subjected to a turbulent flow. And then we have a hot wire anemometer that can be used to measure the speed in the wake at different heights beyond the sign. This allowed us to get information on the Strudel number, which will impact the shedding frequency of the sign, as well as the drag coefficient for this type of structure. We also use these results to validate a computational fluid dynamic and FEM model that was used to confirm what we were seeing and propose potential modifications. So if we look at the analysis of the field data, we can see an impact of the wind speed and the direction on the spectral energy response. So what you see on the left is the spectral energy versus frequency for wind speed. So all of these different events are wind normal to the sign, but there's a varying wind speed. And you do see 2 peaks, one at the first natural frequency and one at the second. But what you'll notice is that the magnitude of this spectral response does not vary linearly with wind speed. You'd see large peaks at particular wind speeds, and it's not necessarily scaling with the increase in wind speed. On the right, you see the same thing, but for events that are approximately the same wind speed, but occur at different directions relative to the sign. So close to 0 and close to about 180, those are 360, those are normal. Here you're seeing a variety of directions relative to the sign. And we see that different directions do have different resonant effects in terms of amplifying the response. So what this told us is that there is a dynamic interplay between the wind and the response of the structure. And particularly, we're interested in how the variation in wind speed might play a role here. And so if we take our Strudel number that we got from our SAFL tests and combine it with our field analysis, for those different events, we can plot the natural frequency of the structure. So that's these square and star or square and X's versus the expected shedding frequency, which is a function of the straw number, the speed, and the wind direction. And we notice that these start to align. 7 meters per second, you get this overlap of the shedding frequency and the natural frequency of the sign. This wind speed is a pretty typical wind speed. And so this is why we're seeing the amplification of the response at this particular wind speed in those previous plots. The natural frequency of the sign is quite low. For this type of structure, it's about 1 hertz. This is a function of both the connection as well as the weight of the sign. And so by adding this additional mass, you're aligning this natural frequency and getting this vortex shedding response. So if you wanted to do any modifications, this is what you would really need to address in order to limit the vibration, either adjusting the stiffness by removing that type of breakaway connection, or adjusting kind of the mass for the height of the sign. So in conclusion, for both sign structures, wind-induced vibration was a key to understanding behavior. Again, in the US, this type of behavior is not addressed for these types of roadside signs. Only recently, in the most interim edition of the AASHTO code for sign structures, did they start to consider that DMS might need additional analysis, but they didn't say how to do that. And then for the DMS, we showed that we needed this dynamic analysis to characterize the fatigue demand, which required the generation of demand wind forcing functions. And then for the RICLIS, we found that vortex shedding was the predominant wind loading phenomenon. And so any modifications should target this, this effect. This project, I didn't do this alone. There was a significant number of faculties and students that worked on this. The Nicole Finley, highlighted in maroon, was the primary student on this project. And I also wanted to thank a bunch of staff that helped, as well as some students in the field. And with that, I'll open up to questions.
Well, thank you so very much to both of you. So we'll open it up to the audience for questions. So one thing I'm going to do is pause the recording so that our audience can speak freely and ask their questions with that. So